have Ashish Gupta as our last talk for the day.
Hello. Yeah, can you hear me? Hi, I'm Ashish Gupta. I'm a PhD student at ESO, working mainly with Anna Mutelu and some other collaborators who I will present the work with in this talk. And today I'm going to talk about influence of infalling streamers on mass accretion rates. And I thank the previous speaker for setting up the base. Um, somebody had to show this plot in this conference. So this is the traditional view we have of low mass star formation. I'm sure you have seen this many times. I just want to point out that we traditionally assume that star formation starts by collapse of these isolated spherical cores. And overall, we assume that the star formation process is very axis-symmetric. And we also think that these more evolved classes, especially like class 2 stages, where we expect or used to think that a lot of planet formation happens, we also think that these are isolated systems which evolve in isolation from the environment. But we know that there is also environment, and we know that these YSOs, denoted by these circular markers here, are moving in these large-scale molecular clouds, and these clouds are highly structured in nature and stuff. So maybe this environment can break this axisymmetric assumptions we had. And that's what we see in simulations, and we have been seeing in simulations for a long time. Particularly, people are seeing these streamers, which are these elongated channels of infalling material. So the material comes from much further away and falls within these channels onto the protostars. And with increase in sensitivity of interferometric observations, we are also seeing this in observations now. So, and we are seeing this in sources at different evolutionary stages, from class 0 to class 1 to the famous HL tau streamer, and to now also around class 2 sources, which we assume to be isolated. These streamers, especially at later stages, can significantly affect the physical and chemical properties of these protostars. And this can explain some of the open problems we have in star and planet formation. For example, it can explain the apparent mass budget problem of class 2 disks, where class 2 disks seem to not have enough mass to form observed population of planetary systems. So these streamers can bring in the extra mass. It has also been shown to be able to reproduce the observed distribution of mass accretion rates, and that's what I'm going to talk about for most of my talk now. It has also been shown that it can form some of the observed disk substructures like vortices and rings, which can have an implication on planet formation. The infalling material can be totally dynamically unrelated to the original protostellar system, so it can have a different orientation of angular momentum, which can naturally cause misalignments in the disks, which can be inherited by the planetary systems. It has also been suggested as one of the possible explanation of the observed chemical dichotomy among meteorites in solar system. It can explain the disks around very old systems. It can recently Andrew Winter and collaborators show that the energetics are also enough to explain the observed turbulence levels in the disks. And finally, it can even change the apparent evolutionary stage of YSOs. So Michael Kupfermeier and collaborators last year showed that a class 2 source undergoing this infall may appear less evolved if we use like simple like bolometric temperature or SEDs as a classification method. This which can have, I think, big implications on our population studies of YSOs. Okay, now more about accretion rates, because that's the topic of the conference. There has been this idea in literature for many years now that we see, and somebody asked in the audience for the last talk, that if there's any correlation between mass accretion rates and stellar mass. So there is, I think, and it's mostly consistent along different star forming regions, that mass accretion rates scale is proportional to square of stellar masses. And people have discussed that this is exactly what you would expect from Bondi-Hoyle type infall. So I mean, okay, we are talking Bondi-Hoyle is more infall onto the protostellar system, and this mass accretion rate is mass falling from disk to the protostar. But maybe there is some connection between these two. And I will also come back to this later in one of observational results. But here you can see that the mass infall rate is basically depends on some environmental parameters and a square of stellar mass. Another idea in which this infalling or axisymmetric infall can affect mass accretion rates is by inducing disk instabilities and causing accretion bursts. So this has been shown, for example, by Jensen et al. 2018 and Kufamine et al. 2018, where this infalling material can be irregular and also induce instabilities. And for example, in this particular source, the accretion rate jumped again because there was at some point another streamer feeding the system. But is there any observational evidence? I mean, we have been seeing this from simulations from quite some time. And this is what I'm going to talk about. But first, we need to characterize streamers. We have been characterizing accretion rates for many years now, but not so many years for streamers. And to do this, we developed this code called TIPSY, which stands for Trajectory of Infalling Particles in Streamers Around Young Stars. So basically, we fit infalling trajectories to the observations of streamers to first check if they are really infalling material or not, and to characterize their dynamics. So as a test case to show how TIPSY works, I will use ESCRA, my favorite source. This is a moment one map showing the potential streamer and 2 disks here. So it's a binary system. And this is the same data set in 3D position velocity diagram. So it's RA, declination, and radial velocity. So this column here, which is confined in RA dec, but extended in radial velocity, is basically emission from the protoplanetary disks. And this structure here corresponds to this streamer, which we want to fit. So the first step of TIPSY is to isolate the streamer emission from the rest of the cube. For this, we use some velocity position cuts to select this subcube. And then we use a clustering algorithm to remove any noisy emission in this subcube, and we get this clean, isolated streamer emission. Then essentially what we have is a point cloud, and we want to compare it to theoretical trajectories, which are curves. To make the comparison more straightforward, we simplify streamers using these intensity-weighted means and standard deviations, which are the red squares and their error bars. And then we fit the streamers with infalling trajectories. And to convince you that the fit is actually good, and I'm not picking a good projection, this is the fit in 3D. So the black line is the best fit. Each layer is basically one channel. The 2 columns are emission from the 2 disks, and so on. And now we can start to analyze streamers around erupting sources. So this is the paper which was mentioned in the last talk, led by Antonio here, where we did the first observational study on relation between streamers and accretion bursts. So we discovered this streamer around FURE. So this is more or less the environment looks like in CO. And we found this elongated structure. This is position velocity diagram along this structure. And the green line in both of these maps are the best fit from TIPSY. So we could very well fit both the morphology as well as velocity gradients simultaneously using infalling trajectories using TIPSY. And because with TIPSY we know we can characterize the dynamics completely, so we can get infalling timescale, which we can combine with the mass estimates, which we can get from this combining CO as 2 to 1 and 3 to 2 observations. Using these, we can get some estimates on the mass of observed streamer. We can divide this by infall time to get infall rate, which we got around of the order of 10 to the power minus 11 solar mass per millilinear, which is quite low to sustain the accretion we observe, but maybe it's still enough to induce instabilities. We don't know. Or it could also be like the streamer which we are seeing now is a remnant of more massive streamer which originally triggered the outburst, and we are just seeing the fading away of the streamer. Another interesting source, M512. So this was the first detection of streamer in continuum emission, and I think it is the only detection, also because somebody asked in the last talk. Here is C18O moment 1 map, and the contours are continuum emission. And this is the, again, position velocity diagram along the streamer. And again, the green curves are the best fit by TIPSY. So again, we can reproduce both morphology and velocity gradient simultaneously using infalling trajectory. And we can play the same game. We can estimate mass using continuum emission, infall time using TIPSY fits, and we can get infall rate, which is few orders of magnitude larger than the previous streamer, which makes sense because this is really massive streamer because it's visible in continuum. And, okay. And we also did some literature review, and we found that this is a known outbursting source, and this is like Weiss curves, and there have been some peaks of outbursts, which which may be due to infall, but that's still, we need higher resolution ALMA data. So give us time. Okay. So far I just showed two sources in this observation, but I think what we really want to know is like how this works over the population of disks and how to study that. So these are some works which I'm involved in, but we need more data as usual. So this is the work led by Andrew Winter, and the paper is submitted. So these are the protostars in Lupus clouds. In this work, we divided the protostars into two categories, one clustered, which are basically here in Lupus 3, and one more distributed population. And we tried to find any relations between their spatial distribution and their mass accretion rates. And for example, among things which we found like for the clustered population, there's a strong anti-correlation between separation from the center and the normalized mass accretion rates, where the mass accretion rates is normalized by square of stellar mass. So as I showed in the Bondi-Hoyle accretion, that you would expect that the mass accretion rate is a function, or infall rate is a function of environment into stellar mass square. So if you divide it by stellar mass square, you should, in principle, get the effect of environment. And this is more or less what we see. And this is statistically significant with a p-value of 0.014. And we found similar statistically significant relations in the distributed populations. And our results strongly suggest that environment is influencing mass accretion rates. Another way we can do this, especially for more evolved sources, is ideally we have mass accretion measurements of many sources, but we don't have infall measurements. And for that, we need an ALMA large program. And that's what DECO is. So DECO is an ALMA large program led by Ilse. So the program was designed to study disk chemistry. So that's why they were moderate resolution observations. But because they are moderate resolution, they can also reveal large scale structures. And there were 80 sources with mass accretion rates ranging from 10 to the power minus 6 to 10 to the power minus 10. So this can be the data set to test this. So now I will show very preliminary results from DECO. And it's like imaging routines are still being optimized and stuff, so it's really preliminary. So these are all CO moment 8 maps. This is for chameleon. So for some sources are still missing, but we really see large scale structures around half of the sources. Some are more prominent, some are less faint, but again, the imaging is optimized to study the disk. So if we really re-image the data to highlight large-scale structures, these structures will pop up more. Then lupus. Lupus is, let's say, one of the cleanest regions, but still we see really messy sources and some sources with faint structures around them. Taurus, most of the data has not been delivered, but still 2 out of 4 sources have some mess going on. And finally, the monster, Rho-Fucus, where almost every source has something going on. There are probably just 2 clean disks, but there's a lot happening. And interestingly, it's also the youngest region in the sample. So that's it. My take-home messages is observations and simulations suggest that infalling streamers can influence mass accretion rates along with planet formation. And upcoming population studies will really allow us to quantify extent of this influence. That's it.
So I really like streamers, so this is great. The problem with the Padoan Bondi-Hoyle accretion is that you can show in several cases that it's completely inadequate to get the accretion rates. So for example, stuff I did many years ago with Aurora Cecilia Aguilar, we looked at Trumpler 37, which has very typical class 2 accretion rates, but it's sitting in a low density H2 region. So the density is low, and because of the sound speed at 10,000 degrees, you know, you're like 4 orders of magnitude away from what you need. So in general, I don't think that's, you know, Bondi-Hoyle, I think, is more important for massive stars, but it's not going to explain, I don't think, the class 2 accretion rates. And so when you talk about environment having an influence, the question is, in my mind, which way does it go? That is to say, if you have a dense environment, you're more likely to have younger stars that have more, maybe in an earlier stage and might have higher accretion rates. So maybe you could address that.
So in this particular study, what we did is we did the same analysis for disk masses and stellar masses. So we thought that, let's say we don't rule out the age effect or the younger sources effect, but we don't see correlations at all for disk masses. And if it was just age effect, you would see that disk masses also have same correlations. So the fact we don't see disk masses change with environment, but we see accretion rates change with environment, so probably I think gives us more hint that it's less of an age effect and more of the environment effect. Also, one reason why we don't see disk masses change as much as disk masses are basically time integrated quantities, and accretion rates are in some sense instantaneous quantities. So yeah, that should be more sensitive to age. So this is why we think it's more of environment than age.
In the middle, Adolfo.
Hi, Ashish. Great talk. Thank you. So I do have a question about this as well. Are there, when looking at how correlated this separation is with this normalized accretion rate, did you account for uncertainties in the stellar masses and the potential for the instantaneous accretion rate to be non-representative of what the range of accretion rates might be in the target? So even just by some assumed, maybe it varies by a factor of half or something, and how might that impact your correlation?
Yeah. So I think we didn't account for that in correlation. I may be wrong. I think we should contact Andrew, or I should read it. I can get back to you. I think we also tried to fit it a bit, and I think in that case we accounted for uncertainties, but not in correlation coefficient. But I can double check and I can get back to you on this. Yeah.
Okay, we have a question from the ether.
Yes, Eleonora Fiorellina is asking two questions. I'll read out the first one. What is the typical uncertainty of the infall, of the mass infall you get for streamers?
So I would say it's an order of magnitude estimate. I think the uncertainty is mainly dominated on the mass side, not so much on the infall time scale, because we can actually characterize the dynamics very well. But when I started estimating masses, I was like, oh wow, it's so complicated, and you have these partition functions which can be different if you take different catalog. So I would treat them as order of magnitude estimates. But I think if you have multiple line transitions and multiple molecules, you can really nail down those as well. But so far, the observations we have, we really see streamers in very few traces.
Okay, I'll read out a second one, if that's okay. MHD winds and viscosity models for class 2 assume the disk mass is set and can only decrease with the time. If streamers are happening always, and even for class 2, are your results suggesting current models which explain, for example, the relation between accretion rate and disk distribution to not be correct?
I would say it's not like infall is happening in isolation. I think there's I would say that I would just say that disk evolution is more complicated than just viscous disk or just MHD winds or just infall. I think it's, I would say that in the inner disk, I guess, where mass exchange, I think maybe angular momentum transport processes within the disk play more important role, but the overall mass and overall energetics of the disk itself are probably more set by their initial conditions and the environment. But yeah, I think we really need more observations and more theoretical studies to nail it. And, yeah.
Thanks. In astronomy, we often don't know the third coordinate, right? And in particular here, we don't know whether the structure you observe is in front or behind the star. So here's a silly first question. Are you not confusing inflows with outflows? Is it possible that I'm just not quite understanding how exactly you're doing it. you sure that these are not outflows, at least in some of the cases?
Yeah, so yeah, I think that's why we really need to do this. Like, I mean, it's not 3D in the way you meant, but fitting velocity gradient and morphology simultaneously. So fitting morphology allows you to constrain the velocities on plane of sky, because your velocities on plane of sky would determine what is the curvature of the streamer as it looks. And then when we combine it by fitting line of sight velocities, give you more or less the complete picture. But going back to outflows, I think you will have, for example, if the outflows are not on plane of sky, you will for sure have higher velocities because they will be unbound. And in this, you will not get the bound solutions. And if the outflows are on the plane of sky, then their morphology will be very different because they will not have the curve because they will go straight. So I think that's more or less how it will be. But I think ideally, I would want to fit some synthetic observations with TIPSy to really test like what parameter space can be ruled out and what we cannot. Yeah, so so this velocity is smaller than the Keplerian disk. So this is really bound material in that sense.
Okay, while we move some chairs around, one more question.
Thanks for the nice talk. I'm curious to know that in your fitting algorithm, did you consider any effects of the magnetic fields? Because given the velocity is very lesser than the speed of the Keplerian disk, so, and do you think that the effects of magnetic field can impact the fitting?
Yeah, so in this fitting, we just assume gravity and nothing else. I think for certain environments, magnetic fields may play a role, but I think for these low mass stars, it should be okay, and low density environments, it should be okay. I'm not sure. But I think something which probably plays even bigger role, which we don't account for, is the tidal force. So for example, if you have a binary, at some point you cannot assume a single source of gravity. So I think, so there is some scope in making the fitting models more complicated, but then there's also con, then you can fit anything if you have enough free parameters. But yeah, like at some point, we should look at including magnetic field and magnetic forces in this. Thank you.
Thank you.
Okay, let's thank our two speakers for the afternoon.